Hello guys, today we are going to learn a very important organic name reaction which is Hell-Volhard-Jelinek reaction, which is abbreviated as HVZ reaction. This is Hell-Volhard-Jelinek reaction. Okay, first of all, what is the reaction? This is the reaction of an alpha hydrogen containing carboxylic acid. This is an alpha carbon of carboxylic acid with respect to the carboxylic acid. This is alpha hydrogen containing carboxylic acid. Okay. On treatment of this substrate by bromine and catalytic amount of phosphorus, and then work up by water or hydrolysis, you will get this product. Okay. The product is this is your alpha carbon. The product is alpha halocarboxylic acid. This is alpha halocarboxylic acid. Alpha halocarboxylic acid. Particularly, this is alpha bromocarboxylic acid here when bromine is used as the reagent. Okay. So this is the reaction of alpha hydrogen containing carboxylic acid to form an alpha halocarboxylic acid on treatment with bromine, catalytic amount of phosphorus and work up with water. Okay. First of all, we just considered the mechanism of the reaction. Mechanistically, the reaction can be explained as follows. In the first step, this catalytic amount of phosphorus reacts with bromine molecule to form phosphorus tribromide, PBr3. Now, the PBr3, this is actually the catalyst of this reaction. In the first step, carboxylic acid reacts with PBr3. Oxygen donates its electron pair here, and this oxygen attacks at the phosphorus atom. Bromine leaves the substrate, leaves the reagent. As a result of that, you will get oxygen, phosphorus. This is PBr2. RCH2CO PBr2, double bond oxygen. Oxygen, formal charge of oxygen is plus here. Definitely, because oxygen has 5 electrons here, 1, 2, 3, 4 and 5. Next, in the next step, Br minus, the Br minus which actually leaves the substrate now attacks at this positively polarized carbon, attacks, and this pi bond is taken out by the oxygen atom. So you will get bromine here. Now in the next step, oxygen actually forms the double bond with carbon, and this PBr2O minus, this leaving group actually leaves the substrate. So the leaving group here is PBr2O, and then this hydrogen is here. So PBr2OH, this is the leaving group. Look at here, this is a very good leaving group, because in this case phosphorus has a vacant d orbital and oxygen has lone pair of its own. So oxygen can donate the electron pair by backbonding to form phosphorus oxygen double bond. This phosphorus oxygen bond is very stable, very strong. Bond energy of this phosphorus oxygen bond is very high. So this is a good leaving group. PBr2O minus, this is a good leaving group which leaves the substrate from here. Now the substrate we have RCH2, this is RCH2, C double bond O, C double bond O and Br, bromine. This is actually acyl halide actually, acyl bromide actually here. This is acyl halide. This is acyl halide, or particularly here it is acyl bromide. Next step, in the next step, tautomerism occurs here. 2 hydrogen are acidic here, due to the presence of the electron withdrawing keto group. The keto group has strong minus I effect. So this tautomerism occurs here. So this is the enol form of this acyl halide. Now with this enol form, the bromine molecule reacts. The bromine molecule reacts with this, the enol form of the acyl bromide. Look at here, the reaction occurs in this way. The oxygen donates this electron pair and the pi bond attacks from the alpha carbon of acyl bromide. So the alpha carbon attacks at bromine molecule. Bromine has del plus del negative center. This is dipole induced dipole interaction. Due to the presence of this induced dipole, bromine becomes delta positive and this bromine becomes delta negative. So this carbon attacks from this alpha position, you will get RBr, this compound. This compound is known as alpha haloacyl bromide. This is your alpha haloacyl bromide. Alpha haloacyl bromide. Acyl halide or acyl bromide? Acyl halide. This alpha haloacyl halide now reacts with another molecule of RCH2CHH, like this. The lone pair of oxygen attacks here, the Br minus leaves the substrate. So we will have an ester-like intermediate. This is definitely the ester group. This is an anhydride-like intermediate. This one is anhydride-like intermediate. This is an anhydride, COO. So look at here, R, C Br, C double bond O. This is your C double bond O. This oxygen attacks here. This is your oxygen, this two oxygen. Then CO, CH2R. So this portion actually, this one, and this portion of the molecule actually goes in this portion of the substrate. Okay, in the next step, Br minus attacks here. The Br minus, there are HBr molecule. One HBr molecules evolves here, and one HBr molecules evolves from here, expel out from here. So Br minus attacks at this carbon. Now oxygen takes its electron pair. When the lone pair of oxygen backs, this portion of the molecule leaves. So actually the molecule gets fragmented into two parts. This is your RCHBr. This is your RCHBr, C double bond O, O minus, and this portion of the molecule is actually this one. I have written this molecule here and this part of the molecule here. So this is your RCH2CO, and this bromine attacks here. So this is your bromine. This part of the molecule is here. So our product is actually on workup of this molecule, this alpha halocarboxylic acid, the salt of alpha halocarboxylic acid, on treatment with water gives us the actual product of this reaction. The product is alpha halocarboxylic acid. This is your alpha halocarboxylic acid. But we take a close look of the other portion of the molecule. The other portion, this portion of the molecule is actually alpha halo. This is your acyl halide. Look at here, these two molecules are actually same. This is your acyl halide, again this is your acyl halide. And look at here, this portion actually tautomerizes to form the enol form, this portion tautomerizes to form the enol form, and this portion actually reacts with bromine as the same way in the previous case, reacts with bromine to form the alpha haloacyl halide. This is your alpha haloacyl halide. So this portion of the mechanism is actually identical with this portion of the mechanism, and I have written in this fashion, this alpha haloacyl halide actually recycles. This alpha haloacyl halide actually goes here, then it reacts with another molecule of carboxylic acid to form the anhydride-like intermediate, and after the attack of Br minus, it will form the alpha halocarboxylic acid. So in this way the reaction will recycle. So actually this alpha haloacyl halide and the acyl halide, these two are the most important substitute for the most important intermediates for the success of this reaction. One is acyl halide and other is alpha haloacyl halide. Now consider the question, why catalytic amount of phosphorus is required for this reaction. Look at here, after the formation of acyl halide there is no role of phosphorus. Look at here, in the first step PBr3 reacts with this one, PBr2 here, Br minus attacks here. Now this portion, phosphorus involving portion, actually leaves the substrate. This is a good leaving group. I have already said this one is a good leaving group. So after the formation of acyl halide there is no function of phosphorus. इसी acyl halide तैयार होने के बाद phosphorus का कोई काम इसी रिएक्शन में नहीं है. So only catalytic amount of phosphorus is required for this reaction. Okay. Now if we critically review this reaction, if you review this reaction critically, we will find many facts. If we treat this substrate RCH2COOH by bromine, of course bromine in presence of say PCl3, phosphorus trichloride. This is your PCl3, and then work up by water. What will be the product here? Of course, the product will be alpha bromocarboxylic acid, not alpha chlorocarboxylic acid, because this is the catalyst. It has the only function to produce the acyl halide, and this acyl halide is not actually the product of this reaction. This acyl halide part will produce the alpha haloacyl halide, and then it will recycle. So this portion of the molecule, this carboxylic acid, actually produces the products alpha halocarboxylic acid. So if we use PCl3, the intermediate will be the acyl chloride, but then this acyl chloride will react with bromine molecule to form the alpha bromoacyl chloride. When PCl3 is used, the analogous intermediate of this one is this one. Of course, bromine here. So on reaction of this molecule with another molecule of RCH2COOH, it will produce the product. RCH, bromine here, and COOH here. This is your product. So no chlorine is here, definitely it is bromine here, because PCl3 is the only catalyst of this reaction. Okay. Next we consider the application of this reaction. Let us find the application of this HVZ reaction. This reaction has many synthetic applications. Number one, let us start from CH3COOH. This is your acetic acid, CH3COOH. If you treat this molecule by bromine in presence of catalytic amount of phosphorus and then work up by water. You will get CH2. Let us take chlorine in presence of bromine. Generally fluorine and iodine does not participate in this reaction. Only chlorine or bromine can be used. Okay, ClCH2CHH. Now this compound can be, this is your alpha chlorocarboxylic acid. This compound can be, compound can be used in very synthetic purposes, or this compound can be converted into different types of compounds. Number one, if we treat this compound by aqueous KOH, aqueous potassium hydroxide. Now obviously the chlorine atom will be replaced by OH minus, so your product will be CH2CHH and this is your OH. This is your alpha hydroxycarboxylic acid. Next, actually this molecule is nothing but glycolic acid. This is actually your glycolic acid. Okay. Next, this substrate can be used for the reaction like this. If you treat this molecule by excess of ammonia, in ethanolic medium, in ethanol, then the enriched lone pair of nitrogen attacks here and chlorine will leave the substrate. The product will be CH2NH2. This is your CHH. This compound is nothing but glycine. This is your alpha amino acid, glycine. Look at here. If you treat ammonia in aqueous medium, there is a chance of formation of the amide because of the reaction of CHH group with ammonia. But if you use excess amount of ammonia in ethanolic medium, preferentially the lone pair of nitrogen attacks here to substrate the chlorine from here and you will have glycine molecule. Now, if we treat this molecule by say cyanide, like sodium cyanide, maybe potassium cyanide, then you will get CH2CHH and Cn minus will replace Cn. And on treatment, on acidic hydrolysis of this compound, this is your alpha cyanocarboxylic acid. On hydrolysis, acidic hydrolysis, this molecule will produce CH2CHH and this one definitely CHH. The name of the compound is definitely malonic acid. So this acidic acid can be converted into different types of compounds, glycolic acid, glycine, malonic acid, etc. By the intermediate formation of this alpha chlorocarboxylic acid. The first reaction is actually HVZ reaction. Definitely this reaction is HVZ. This is the very good application of HVZ reaction. Next, you can apply HVZ reaction in other ways also. Look at here. Next, or the intermediate compound of HVZ reaction, this is your RCH, this is your COBr. As I have written earlier here, this is your alpha halo acyl halide. This is your alpha halo acyl halide. Alpha halo acyl halide. Now this molecule can be converted into different types of compound. If you treat this molecule by simply ammonia and excess of ammonia, lone pair of nitrogen will preferentially attacks at this carbon, this because this oxygen is del negative, carbon is del positive, and Br is a good leaving group. So lone pair of nitrogen will preferentially attack here because this is the hard positive center. So you will get RCH, bromine, then CONH2. Your product is alpha bromoamide. Your product is nothing but alpha bromoamide or alpha haloamide. Alpha haloamide. Next, if you treat this molecule by say alcohol like C2H5OH, ethyl alcohol, you will get RCH, this is your CO, then OC2H5. Definitely this one is the ester which contains an alpha halogen. So this molecule is alpha halo ester. And of course, if we treat this molecule by water, you will get alpha halocarboxylic acid as earlier. Okay. Next, this reaction can be applied in many ways. Okay. Look at here. If we have the molecule like say this one. This one is definitely adipic acid. This is a dicarboxylic acid containing 1, 2, 3, 4, 5, 6. 6 carbon dicarboxylic acid. This is your adipic acid. If we treat this molecule by say SOCl2, this is your thionyl chloride, then you will have the product COCl, and then this one is COCl. This is acyl chloride. And if we treat this molecule by bromine only, if we treat this molecule by 2 equivalent of bromine 2 equivalent amount. Look at here. I can specify here no need of Lewis acid catalyst, no need of phosphorus catalyst here, no need of catalyst or no need of phosphorus here. Just recapitulate the mechanism of the reaction. The role of phosphorus was to prepare the acyl halide. This is your acyl halide. So after the formation of this acyl halide, there is no role of phosphorus. Now it will tautomerize to form its enol form, and this alpha position is substituted by this bromine. So it will produce the molecule like this. This is your COCl, then this is your COCl. Okay. Now if we treat this molecule by say ethyl alcohol, if we treat this molecule by excess of ethyl alcohol, it will produce the alpha haloester, the alpha bromoester, this one. Now if we treat this molecule by say alcoholic KOH or methanolic KOH, maybe ethanolic KOH, potassium hydroxide, elimination reaction will occur and two double bond will be formed here and also here, this one. And lastly, if we hydrolyze this one, acidic hydrolysis, you will have the molecule like this. Look at here. This one was adipic acid, and after the treatment of SOCl2 and then by pursuing HVZ reaction, we can convert this adipic acid to, this one is known as muconic acid. Muconic acid containing two double bonds. Okay. Okay. Lastly, let us take another application of HVZ reaction. Say, if we have the substrate like this one, this is your DEM, this is diethyl malonate. This is your DEM molecule, diethyl malonate. Okay, if we treat this molecule by say C2H5ONA, sodium ethoxide, we know this CH2 group, this one is known as active methylene compound. This is an active methylene group. So O- will deprotonate this CH2 group to produce CH minus and C2H5 Na plus. Now if we treat this molecule with say benzyl bromide, this is your PHCH2Br, benzyl bromide, this carbon is del positive center, bromine is del negative here, so minus will attack here to expel out bromine from here. So we will get PHCH2 CH C2H5, then this is C2H5. Now if we hydrolyze this molecule on acidic hydrolysis, these two ester groups will be hydrolyzed, so you will get PHCH2 as it is. Now this is your CH, then CHH, then CHH. Now, if we treat this molecule by, say, bromine only, if we treat this molecule by bromine only, this is again HVZ reaction. HVZ reaction. This is again. And again, look at here, no need of phosphorus here, because due to the presence of this two COOH group, this hydrogen is very acidic. So the enolization occurs very readily. So only bromine is enough to substitute the alpha hydrogen from here. Sorry, the alpha hydrogen here. The alpha hydrogen here. This is your alpha carbon with respect to both the COOH group. Okay. You will get pH CH2. Now C. Then this is your COOH. This is your COOH. And this is your bromine, which substitutes the hydrogen, the alpha hydrogen. Okay, in the next step, if we heat this molecule, on heating, this molecule will undergo decarboxylation, because look at here, with respect to this keto group, this is alpha, this is beta keto carboxylic acid, and of course with respect to this keto group, this one is alpha, this one is beta. This is beta keto acid. So we know on heating, this beta keto acid will undergo decarboxylation to expel out carbon dioxide molecule from here. You will get pH CH2, then C, CH, this is your bromine. This is your red bromine. The mechanism of this step is like this. This one is OH, and on heating, this decarboxylation occurs. These things happens, and the minus over there is stabilized by the conjugation with the COOH group. So this carbon dioxide will evaporate out from here. Now the last step, if you treat this molecule again by excess ammonia in ethanol, definitely in ethanol, C2H5OH, it will produce pH CH2, this is your CH, COOH, and bromine will be substituted by ammonia here. This is NH2 group here. So this is the molecule which is our target molecule. This one. What is the name of this compound? This one is nothing but phenylalanine. The name of the compound is nothing but phenylalanine. We can write, the name of the compound is phenylalanine, which is again an alpha amino acids. Alpha amino acid. This is your alpha carbon with respect to COOH, and this is an H2 group. And pH CH2, this is your phenylalanine. This is actually phenylalanine preparation. This is actually preparation of phenylalanine, which is an alpha amino acid from diethyl malonate. We can carry out this conversion by employing, of course, HVZ reaction. So this is all about HVZ reaction. Thanks a lot. Thanks for watching the video.